When I was at school, they taught me a curious fact about Shakespeare's plays. There are 4 plays of Shakespeare which have another play inside them. In Hamlet and the Midsummer Night's Dream, as I expect you remember, there's a scene where some players come on and act a play. And there's something like that in The Tempest as well. And the whole of the action of The Taming of the Shrew takes place as a play inside another play. So in these 4 plays, Shakespeare was writing a play about a play. Now what corresponds in mathematics is to do mathematics about mathematics. Most of the mathematics that we do isn't about mathematics, it's about something in the real world, say calculating the orbits of the planets, or the speed of chemical reactions, or how long it takes men to mow a lawn or fill a bath, or what have you. But sometimes mathematicians like to stop for a moment and say, what are the mathematical properties of mathematics itself? Let's try and do some mathematics about mathematics. This idea seems to have worked rather well for Shakespeare, and I hope to convince you in the course of this talk that it's a good idea for mathematics to take a look at ourselves sometimes this way. Now let me be historical. The main thing that mathematicians do is to solve equations or solve problems. Let's look at an early example of solving a problem. This is a diagram taken from an Arabic text of the early 9th century. And it's a solution of the equation x squared plus 10x equals 39. Now, I don't want to go too deep into the details of this, but very roughly what happens is we, as the diagram shows, we build a large square whose side is of length 2.5 plus x plus 2.5, and we put a smaller square inside it of whose sides are of length x, and we calculate the area of the whole big square. You can work it out. If x squared plus 10x equals 39, then the whole square has area x squared plus 10x plus 25, which is 39 plus 25, which is 64, which is 8 squared. And so one side of the big square must have length 8, and thus 2.5 plus 8 plus 2.5 equals 8, and so x equals 3. Well, now, when I saw that solution, my reaction, I expect you had the same kind of reaction, was, isn't this a little bit specialized? Suppose you were offering yourself as a mathematician, and somebody said, well, I'd like you to solve x squared plus 5x equals 38 for me. And you said, well, it's a bit embarrassing, but I'm afraid the only equation I can solve is x squared plus 10x equals 39. I think you'd feel a bit silly. Now, the moral is that what we really want is not just a method for solving one particular quadratic equation, but a method for solving any quadratic equation that comes along. Well, people who read that Arabic text, in fact, came to the same conclusion, and they analyzed the method given in the text, and they worked out, over the next 200 years after that text was published, they worked out the general method of solving quadratic equations by completing the square. And they were very pleased with this method. It was a general method for solving any quadratic equation. So they wanted a name for it, and they looked back to the author of that text. His name was Al-Khwarizmi, and they said, let's call this general method an Al-Khwarizmi, because it was him who started it. If you think sandwiches are named after the Earl of somewhere, and Wellington boots after the Duke of somewhere. And so people would say, when they wanted to solve a quadratic equation, let's try an Al-Khwarizmi. By the way, Al-Khwarizmi, his name means the man from the region of what's now called Khwarizm in Soviet Uzbekistan. And this stamp that I have here was issued a couple of years ago in the Soviet Union to celebrate his 1200th anniversary. I was sent this by a mathematical friend of mine in Leningrad. Now, the name came west together with the idea, and it got a little corrupted as it came west. And the modern Western form of the name al-Khwarizmi is simply algorithm. And today we say algorithm, meaning a general method for solving a class of problems. By the way, there was an earlier and slightly more corrupt form of that name came through in the time of Chaucer, and he called these things orgrims, but that name didn't stick. So today we have algorithms, general methods for solving equations, or general methods for solving problems, I should say. Now, back to our quadratic equations. Suppose you hired yourself out as a mathematician and somebody brought you a differential equation to solve. I think you'd feel a little bit silly if you had to say, well, I'm sorry, I can't do that. I've got a general method for solving any quadratic equation, but I can't do differential equations. And there's a moral. What we really want is not just a method for solving some particular class of problems, but a range of methods for solving any of the kinds of problem that might come along. Or better still, what we really want is a method for finding methods for solving problems, so that if you give me a mathematical problem, I can work out what's the way to solve it. So the moral is, what we need in mathematics is a general method for finding algorithms. Now, this idea worked its way gradually into people's consciousness during the second half of last century. The first step towards finding a general method was finding a general language for mathematics. If you look at any mathematical textbook, you'll see a number of symbols there. You'll also see quite a lot of text. People said, well, an English text is not really as precise as a piece of mathematical symbolism. And mathematics should be absolutely precise all the way along. So we ought to find a formal language for expressing all of mathematics. Now, in the early days of these things, people had to start from from the formal languages that they knew, and that really meant they had to start from algebra. And here's an example from a book published in 1854. It's an attempt to turn an argument into mathematical notation. And you see at the top there are some phrases in English, and down at the bottom is the mathematical version. And you're supposed to be able to show that the argument is correct by solving some mathematical equations. In the early days, the people who tried to do this translation of mathematics into symbols had rather a hard time of it. Nobody else took them seriously. And I think we can see why, because there wasn't really much that one could do to advertise it. What's the point? And in fact, if you look back at that slide I gave you there, and if you look closely at the text, you'll see that in fact this argument is a proof of the existence of God turned into symbols. And I'm afraid that kind of choice of example didn't do much, didn't really help these people in the mathematical community. Mathematicians said, look, we want something serious here, something that will help us mathematically, and not little bits of theology. Of course, today, nobody has to do any advertising of formal languages. We use them all the time. If you've ever programmed a computer, then you used a formal language, because computer programming languages are a kind of formal language. So nobody has to justify using these things today. But back in the late 19th century, it was different. The man who did that piece of argument that I showed you was George Boole, by the way. He's better known for his Boolean algebra, which is now used for analyzing computer hardware. To my mind, the main advance in this direction came with the work of a German mathematician, David Hilbert. I think of Hilbert as a sort of Edison of mathematics. He was a genius at thinking of clever things to do and showing how to do them and making things work. And a lot of the things we do in mathematics today, we do them because Hilbert showed that one could do them. And in about 1900, Hilbert got interested in this program of turning mathematics into symbols. And his idea was roughly this. If you watch a mathematician at work, what he's doing is writing symbols on a page. Some of them will be mathematical symbols, some of them will be words in English or German, but he's writing them on a page, and he looks at what he's written and he writes some other things down below them in the light of what he's written at the top of the page. And there must be some rules there, Hilbert said. There must be some rules for making correct deductions or calculations. And sometimes a mathematician makes a mistake and he crosses it out. Well, there must be some rule that he's broken when he makes a mistake. And Hilbert's idea was, suppose we translate all of mathematics into a precise notation, then we can analyze what are the rules for manipulating this formal language. What are you allowed to do as a mathematician and what's forbidden? Here are some remarks he made about this in 1927. As he said, in mathematics what we consider is the concrete signs themselves. All the propositions that constitute mathematics are converted into formulas. He means he wants to convert them into formulas so that mathematics becomes a list of formulas. And he says the game with formulas is carried out according to certain definite rules in which the technique of our thinking is expressed. Hilbert also noticed something that we're going to be using later that helps our analysis. Really one only needs one kind of algorithm, and that is an algorithm that will answer yes-no questions, where you're given a statement and you have to work out whether the statement is true or not. Now, I won't go into the details of how other kinds of algorithms can be reduced to this one, but roughly speaking, if you're trying to solve an equation, you can ask, is there a solution greater than 0? Is there a solution greater than 1? Is there a solution greater than 2? And so on. And you can gradually pin down the solution that way. From now on, I'm going to concentrate on algorithms that are for answering yes-no questions. Hilbert's hope was that his general approach to mathematics, by turning everything into formulas and analyzing the rules, would give us an algorithm that would enable us to solve any yes-no problem about the natural numbers, 0, 1, 2, 3, and so on. Now, there are some grand old problems about the natural numbers that can be put into this form. For example, there's a thing known as Goldbach's conjecture, which states that every even number from 4 upwards is the sum of 2 prime numbers. For example, 4 is 2 plus 2, 6 is 3 plus 3, 8 is 5 plus 3, and so on. And a lot of people would very much like to know whether this conjecture is true, whether it's really true that every even number from 4 upwards is the sum of 2 primes. And a lot of people have worked very hard on this question. Well, if Hilbert's method was going to work, then we would be able to answer this problem simply by writing down the statement of Goldbach's conjecture in our formal language for arithmetic, and then applying Hilbert's algorithm to see whether the statement is true or not. Not everybody was happy about that possibility. Some people said that this is going to take all the creativity out of mathematics if you just get your answers by turning a handle. But those people had nothing to fear, because a clever young man called Kurt Gödel came on the scene and showed, by analyzing Hilbert's notion of formalizing mathematics, that there could not possibly be an algorithm for settling all questions of arithmetic. Here is how Gödel himself put it. He said, there is no algorithm for deciding relations, that means statements about numbers, in which both plus and times occur. Gödel published this result in 1931. It's one of the most startling results of all mathematics. It's very hard to see just looking at it how on earth one will prove it. But in fact what Gödel did was to analyze the notion of an algorithm and show that if there was an algorithm for solving problems of that kind, then the algorithm could be used for solving problems about itself, and that would get us into contradictions. Well, you might suspect that Gödel's negative result there would have a dampening effect on research in this area. In fact, quite the opposite. In the first place, Gödel only showed that there is no algorithm for solving all problems of arithmetic, but there's plenty of room left for algorithms for solving this kind of problem or that kind of problem. One can move on to cubic equations and so on and so on. And so a great deal of energy has gone into the problem of finding algorithms for solving this type of problem or that. And second, Gödel's analysis of what was involved in performing an algorithm was taken up by other mathematicians, and after about 15 years' research by various people, it turned into the first electronic digital computers. Those are machines which perform algorithms. So I don't think we need to be sorry about Gödel's result being a negative one. I reckon that that paper of his has probably had more effect on our lives than any other single paper published in scientific research this century. However, that's not what I want to talk about. You all know what a computer is. I want to talk about something that you probably don't know about, and that is the direction that mathematicians have taken in their abstract thinking about algorithms since Gödel's work. Now, one of the effects of Hilbert's approach was that many mathematicians said the real substance of mathematics lies in the formulas and the rules for operating with them. And in the 1930s and 40s, there were quite a number of mathematicians who were almost frightened to talk about the meaning of the formulas, because they felt now the meaning is something a bit suspect. It's not something that's there in the symbols themselves. And really, what we can handle mathematically is the symbols. But by the time the 1950s came, there was a reaction against that. And I must say, I think a very healthy reaction. If you're looking at a formula in a formal language, and you're trying to work out whether it's true or not, and you're trying to find a method for calculating whether it's true, well, it makes sense to look at what the formula means after all. Because that's what we're really after. We want to know whether what it means is something true. And also the meaning is very often a cue to where to look for a way of solving the problem. If you're refusing to look at what the formula means and you're just looking at a string of symbols, then you're going to be throwing away a lot of your intuitions. And so people said, why don't we look for ways of finding algorithms which use the meanings of formulas, which use the sense of them? One of the pioneers of this more modern approach to algorithms was a French scholar called Roland Fréisset, who wrote a number of papers in the 1950s, which we now regard as pioneering works in this field, though at the time I think he didn't always get the credit that he deserved. Well, I want to make a break there, and in the second half of the talk I want to study Fréisset's contribution. In the second half of my talk, I want to look at some of Roland Fréisset's ideas about the meanings of sentences in a formal language, and I want to show you how these ideas can be used to produce algorithms to solve problems. Fréisset began with the question, what is a sentence for? Now, sentences are either true or not true, and we use them to make distinctions. Like I say, that's red, when I'm talking about something which is red, and that's to distinguish it from something which is not red. So, Freyse asked, how do we use sentences to distinguish one thing from another? And the answer that he gave had the form of a game. It's a game between two players, and I'll call them Abelard and Eloise. In the middle of this picture you see two, well, I'll call them structures. They're not anything in particular, they're just pictures I put together. But Abelard is going to try to prove that these two structures are different, and Eloise is going to try to prove that they're the same. The game takes place in steps, and in each step of the game, first Abelard points out some feature of one of the structures, and Eloise has to try to match that feature with a corresponding feature in the other structure. And so as the game proceeds, Abelard will have pointed out more and more features, and Eloise will have matched them with more and more features. And Abelard wins if there comes a point before the end of the game where the features that have been picked out in one structure don't fit the features that have been picked in the other structure. Abelard always chooses from whichever structure he wants, and Eloise chooses from the other structure. For example, with these two structures here, Abelard might start by saying, well, there's a black hand in the upper structure. And Eloise would reply, well, there's a black hand in the lower structure too. Then Abelard might say, at the second step, but there's a white hand pointing to the black hand in the lower structure. And then you see Eloise would be stuck. She could say, well, there's a white hand in the upper structure, but she couldn't find a white hand pointing to the black hand. So in that game, Eloise would have lost by 2 steps. Now, Freyse's idea is, let Abelard and Eloise try to play this game, comparing 2 structures. The more similar the 2 structures are, the longer Eloise can keep going. And so we can measure how similar the structures are by how long Eloise can stay alive in this game. Now, I haven't told you what a structure is, and I don't propose to do that. I'm going to look at a particular kind of thing that a mathematician would call a structure, an example of what a mathematician would call a structure. And I shall call these beadings. A beading is a string of coloured beads laid out in a line from left to right. And here are some examples of beadings. They can be finite. In the top beading there are just 4 beads. They can be infinite. In the second beading the string goes off infinitely far to the left and to the right. In the third it goes infinitely far off to the right. The fourth beading, it looks a little curious. That's a kind of abstract beading that you couldn't construct in the real world at all. The idea is this. Take the real numbers and paint all the integers red, but paint all the other real numbers black, and then you would get something like that beading down the bottom. Well, I shall be mostly concerned with finite beadings, and I want to play Freyse's game with these beadings to show you how it goes. I haven't said how this is connected with formal languages yet, but that will come. Now, in these games, the 2 players, Abelard and Eloise, will play by choosing beads. And the beads have got to match in 2 ways. First of all, the matching bead has got to be the same colour as the bead it's chosen to match. And second, the order of the beads in one structure has got to be the same, going from left to right, as the order of the beads chosen in the other structure. So let's play the game where we stop after 1 step. So each of the 2 players is allowed just 1 move. We call this the game of length 1. Suppose that Abelard chooses the top right-hand bead. And Eloise has to match this by choosing a bead from downstairs. Now, here you see she's chosen the middle bead from downstairs, and it's the same colour as the bead that Abelard chose. So it matches. In this play of the game, Eloise has won. Let's play the game again. This time, suppose Abelard starts. You see the A upside down there from the beginning of Abelard's name. Abelard starts by choosing the red bead down in the bottom beading. And Eloise matches it by choosing the red bead upstairs. And again, she's won. The colours are the same. Now, if you look at these two beadings and think about this game of length 1, you'll see that Eloise can always win it, because all she has to do is to find a bead of the same colour as the one that Abelard has chosen, but in the other beading. And since the two beadings both have red beads and black beads and no other colours, Eloise can always win. Now, we have a name for this situation. When Eloise can always win this game, we say that she has a winning strategy. A strategy is a set of rules that tell her what to do to be sure of winning. And so Eloise, as we've seen, has a winning strategy for the Fraisse game of length 1 on these two beadings. Now, we shall say that the two beadings are one equivalent, to mean that Eloise has a winning strategy up to this, up to one move in the game. Likewise, we shall say that they're two equivalent if Eloise can always guarantee to keep going for 2 steps, and so on, 3 equivalent, and so on. So 1 equivalent means quite similar, and 2 equivalent will mean even more similar, and 3 equivalent even more similar than that. Let's play the game now on the same two beadings, but let's run the game for 2 stages. As before, we imagine Abelard picks the top right-hand black bead, and Eloise matches it with the black bead from downstairs. Now suppose Abelard picks the red bead upstairs, and for her second move, Eloise has got to match that downstairs. What can she do? One thing she can do is to choose the red bead downstairs. Now, the colours match. Eloise has matched black against black and red against red, but she's got the order wrong. As you see, the lines joining red to red and black to black cross. The red is to the left of the black upstairs, but it's to the right of the black downstairs. And so the chosen features don't match. And that means that Eloise has lost this play. Well, suppose she chose differently. Suppose she tried to match that red bead upstairs against the other black bead downstairs. Now, the order's right, the lines don't cross, but this time the colours don't match. The red bead upstairs doesn't match the black bead downstairs that she's linked it with. So again, Eloise has lost and Abelard has won. Abelard has shown in 2 steps that there's a difference. And if you think about these two beadings, it's not too hard to see that Abelard can always guarantee to show within 2 steps that the two beadings are different. So Eloise doesn't have a winning strategy for the game of length 2 on these two beadings. And this shows that the beadings are not 2 equivalent. They're 1 equivalent, but not 2 equivalent. Now, at this stage, one can try to calculate how one can tell, if one's given 2 beadings, whether they're 1 equivalent, or 2 equivalent, or 3 equivalent, and so on. And of course, one way is to play the game over and over again, but there must be better ways of doing it than that. For beadings that consist only of black beads, there's a quite simple formula, which I give you here. For any positive number n, 2 finite beadings with only black beads are n equivalent if and only if either they have the same length, the same number of beads, and that number is less than 2 to the n minus 1, or both the beadings have at least 2 to the n minus 1 beads in them. So, for example, if n is 2, the game is of length 2, then the 2 beadings are 2 equivalent if and only if either they both have 1 bead, or they both have 2 beads, or they both have at least 3 beads. So one beading of 3 beads and another of 246 beads would be 2 equivalent. Well, that's shown you some examples of the game at work. Freysse described this game in a much more general setting than the one I've given. I've simply taken beadings as one example of a kind of structure where you could apply the game fairly easily. And Freysse went on to prove some general theorems about his games. I'll state these theorems as 4 beadings, but again they apply in a lot more cases. The first theorem that Freysse proved was this. Suppose we take a positive integer n and we look at the game of length n. So we're looking to see what beadings we can distinguish by the game of length n. What Freysse proved is that there are a certain finite collection of beadings so that every beading is n equivalent to one of that finite collection. Or, to use the jargon, there are only finitely many n equivalence types of beading. We've already seen this for black beadings and the number n equals 2. We saw there that there are just 3 equivalence types. There was, first of all, the beading with just 1 bead, and second there was 2 beads, and third there was 3 or more beads. Those are the only equivalence types. But this is a general theorem, Freysse's finiteness theorem, that for any positive n, there are just finitely many n equivalence types. Next, Freysse showed that if you take a beading and look at some interval inside that beading, like the piece shown in black and red in the top beading here, if you replace that interval by another beading which is n equivalent to it, then the whole of the beading that you get, the replaced piece plus the n bits that you left the same as before, the whole of that beading is going to be n equivalent to what you started with. This is a bit like in arithmetic, where, say, if you've got x equals 2, then x plus y equals 2 plus y. You replace the x by 2, the whole of the x plus y becomes equal to 2 plus y. Freysse's next theorem was what in fact is generally known as the Fefferman-Vaught theorem, because a couple of people called Fefferman and Vaught proved a more general form of this. It's the first result of Freysse which involves calculation. What Freysse showed is, suppose you've got 2 beadings and you've worked out what the n equivalence type of each of those beadings is for a certain number n. Then you can work out what the n equivalence type is of the beading you get by stringing those 2 beadings together, one followed by the other. Now, there are 2 important points here. The first is that the n equivalence type of the string, first beading followed by second beading, only depends on the n equivalence types of the first and the second. We had that from the replacement theorem just now. But the second point is that you can actually calculate. If you've got a description of the n equivalence types of the 2 separate beadings, then you can calculate the n equivalence type of the beading got by joining them together. And Freysse's last theorem about his games was as follows. It's called the normal form theorem. This is the theorem where we start studying sentences of a formal language. I won't describe exactly what the formal language is, but it's the natural formal language for talking about beadings, and it will have expressions that mean x is a red bead, x is a black bead, the bead x is to the left of the bead y, and things like that. Now, Freysse showed, suppose we take any sentence S of this language, then there is a number n with the following property, that we can tell whether S is true in a beading by telling what the n equivalence type of the beading is. If another way of saying the same thing is that if two beadings are n equivalent, then either both of them make the sentence true or neither of them makes the sentence true. And the argument that shows that there is this number actually shows more. It tells you can calculate the number from S. Now you see, this is back to Hilbert's ideas that we were talking about in the first half of my talk. We've written down a mathematical sentence in a formal language so that we can do mathematical calculations on it. And Frese's result here says that from the sentence we can calculate a number n such that we can tell whether that sentence is true of a beading by telling the n equivalence type of the beading. Right, so those are Frese's theorems about his game. Let's use these theorems now to solve a problem, to construct an algorithm. The problem is going to be, suppose we have a sentence in the language which is appropriate for talking about beadings. Can we tell whether that sentence is true for all finite beadings? For example, the sentence might say, there is a leftmost bead. There is a bead at the left-hand end. Now you can see that's going to be true in any finite beading. A finite beading can't go on forever to the left, but there are infinite beadings with a leftmost bead, and there are infinite beadings without a leftmost bead. So the sentence, there is a leftmost bead, is true for all finite beadings, but not for all beadings. Now what we want is an algorithm that will tell us, given any sentence S, whether or not S is true for all finite beadings. Now straight off, it's not at all clear that there can be any way of solving this problem, because there are infinitely many beadings, infinitely many finite ones even. There are beadings of length 1, beadings of length 2, beadings of length 3, and so on. And in our lifetime we can never go through all of them to check whether the sentence S is true in all of them. So it might simply be that there is no method of telling whether a sentence is true in all of them. Nevertheless, Frese found a way of doing it. And the method is as follows. Suppose we take our sentence S. We calculate, by the normal form theorem, a number n such that whether S is true of a beading depends only on the n equivalence type of the beading. Once we have this number n, and we can get it by calculation, once we have that number n, all we need do is collect up examples of all the n equivalence types of finite beadings. And we know by the finiteness theorem that there are only finitely many of them. Our only problem is to catch them all. So how do we do that? Well, let's start with the black beadings, the beadings with no red beads in them. And let's suppose for simplicity that the number n is 2. Well, all black beadings, all finite black beadings, that's important, all finite black beadings can be got as follows. Take one bead, then add another bead to the right of it, then add another bead to the right of that, and so on, adding just black beads until you get to the length you want. So we'll look at the black beadings starting with just one single bead. One single bead gives you one 2 equivalence type. Let's add another bead. That gives us 2 black beads. That gives us another equivalence type. Add a third, 3 beads. That's another 2 equivalence type. Add a fourth, aha! Now, by the Fefferman-Vaught theorem, you can calculate what the two equivalence type of 3 plus 1 beads will be. And it turns out to be equal to the two equivalence type of just 3 beads in a row. Now, you may remember that from a formula that I wrote up before, but in fact we can calculate that from the Fefferman-Vaught theorem. So 4 beads is 2 equivalent to 3 beads. What about 5 beads? Well, 5 is 4 plus 1. 4 is equivalent to 3. So 4 plus 1 is equivalent to 3 plus 1 by the replacement theorem. And 3 plus 1 is 4, which is equivalent to 3. And so what we've shown is that 5 beads is 2 equivalent to 4 beads, which is 2 equivalent to 3 beads. And so it goes on. You can see that adding another black bead at the end here is never going to give you a new equivalence type. So in this way, we can make a complete list of all the 2 equivalence types of all black finite beadings. Suppose we want to list all the types of beadings with red and black beads in them. Well, this is a little bit more complicated because the process for building these up is a bit more complicated. We start with 1 red bead or 1 black bead. And we get longer beadings by adding at the right-hand end either a red bead or a black bead. So there are more possibilities to take care of at each turn. But the same idea applies in principle using the replacement theorem and the Fefferman-Vaught theorem and so on, as we did before. And in this way, we can make a complete list of the 2 equivalence types, or in the general case, the n equivalence types of finite beadings. And the list will be finite. To see whether the sentence S is true in all finite beadings, we only need to look through these finitely many, which we can do. That's not hard. And so we reach our conclusion. Given the sentence S, we can calculate, i.e. there is an algorithm for calculating whether or not that sentence is true in all finite beadings. By the way, I thought it would be nice at this point to give you a list of all the 2 equivalence types of finite beadings with 2 colors. I thought there can't be all that many of them. After all, if there are only black beads, then the number, as we've seen, is 3. So if we allow red beads as well, I thought maybe it's about 14 or 15, and I can give you a chart that shows the whole lot. But when I sat down to make a list, I found it grew longer and longer. In fact, embarrassingly long. And then I thought, well, the whole point of this talk here is that this is something we can calculate. So I went to the computer and calculated the exact number of 2 equivalence types of 2-color finite beadings. And the number turns out to be 96. Which is rather a large number for these purposes. For most sentences that you want to test, you're likely to find that the number n you need to look at is much higher than 2. And the number of equivalence types that you've got to check is going to be very much higher, going into the millions. And there is a moral of this, a moral that comes from this. The approach we're taking will show that there is an algorithm, and it will find an algorithm for us, but it doesn't guarantee that the algorithm will be efficient or fast. Now, that doesn't always matter very much, because once we have an algorithm, we can hand it across to the computer people, and they're very good at speeding up algorithms. You see, it needs 2 kinds of mind here. You need somebody, first of all, to show that there is an algorithm, and then you need the technician to go to work on it and bring it down to a level of efficiency where people can use it to solve practical problems. Now, I would like to give you more examples of algorithms that have been found by using phrase-say games, but I'm short of time and the examples tend to be technical, so I'll limit myself to just one. This is a theorem which was proved back in 1930 by a young Polish scholar called Presburger. You remember Gödel proved that there is no algorithm for settling the truth of sentences about numbers. What Presburger showed is that there is an algorithm for settling the truth of sentences about numbers, provided that the sentence doesn't ever use multiplication. It can use addition and it can use the less than relation, but not multiplication. This is actually rather a serious restriction. It means we can talk about x plus y, we can talk about 2x, because 2x is x plus x, but we can't talk about x squared because that's x times x. So it is a serious restriction. Nevertheless, Presburger showed if you got a sentence about numbers, 0, 1, 2 and so on, which doesn't ever use multiplication, then, well, he described an algorithm which will tell you whether that sentence is true or not. And people have looked at Presburger's algorithm and they've adapted it and adjusted it. And it does seem that one of the most efficient algorithms to do this job that Presburger described is an algorithm based on Freise's games. And now, before I finish, I want to raise a general question here. Why do games appear in all this? As a matter of fact, Freise himself didn't mention games. It was another Polish mathematician, Andrzej Ehrenfeucht, who translated Freise's work into the language of games. Though I think it's fair to say that the idea was fully there in Freise's work in the 1950s. But why games in the first place? Now, it turns out that there is another game lurking in the background of Freise's games. This is a game not for comparing two structures, but for comparing a sentence and a single structure. Again, I can't go into details, but here is an example of the game at work. This is a picture of a function between the intervals 0 and 1. The dark line is the graph of the function f. And on the right of this slide, I've printed the definition of the property that the function is uniformly continuous between 0 and 1. It says for every epsilon greater than 0, there is delta greater than 0, such that for every x, blah, 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 blah. If the distance between y and x is less than delta, then the distance between fy and fx is less than epsilon. Well, if you didn't follow all that, not to worry, nobody ever does first time. This is a definition which we have to teach to undergraduates in second year, and it takes, at a rough guess, 6 weeks to get it into them. So it's quite a complicated notion. But if we turn it into a game, that can help. Let me illustrate this. Let's go back to the slide. The statement, the definition of uniform continuity starts, for every epsilon greater than 0, there is a delta greater than 0, such that, etc. Let's bring in Abelard and Eloise to play another game for us. Abelard will start by choosing epsilon greater than 0, and Eloise must choose delta greater than 0 after Abelard has chosen epsilon. Eloise will win if the rest of that statement comes out true. Now, it says, for every epsilon greater than 0, there is a delta greater than 0, such that. And translating that into terms of games, that means whatever epsilon Abelard chooses greater than 0, Eloise can always choose a delta greater than 0, such that she wins the game. In other words, she has a winning strategy. Well, I slightly oversimplified things there. I ignored the third and fourth lines of the definition. But glossing over that, what we've done is to define what I call the uniform continuity game. It looks like this. Abelard picks epsilon greater than 0. Then Eloise picks a number delta greater than 0. Then Abelard picks an x in the interval 0 to 1, and Abelard picks y in the interval 0 to 1, and Eloise wins if the last sentence of the previous definition comes out true. Now, the statement that the function f is uniformly continuous can be rephrased as follows. Eloise can always win the uniform continuity game. So, the statement that a certain sentence is true about a certain mathematical structure can be rephrased as the player Eloise can win a certain game. Eloise has a winning strategy for a certain game. Now, just to bring us bang up to date on this, two friends of mine at Stanford University, John Barwise and John Etchemendy, recently sent me some software that they use at Stanford for teaching undergraduates. In this software, the computer plays the student at this game I've just described. The computer is Abelard and the student is Eloise. So the student's got to try to win, and the computer will try to stop him or her. This is Barwise and Etchemendy's idea of a typical structure. It's what corresponds to my beadings. My beadings were in one dimension, and they're what they call it a world. It's in two dimensions. But theirs is only black and white, whereas mine used different colors. And so their language corresponding will have notions like cube and tetrahedron and dodecahedron, and it'll have notions like to the left of, to the right of, between, and so on. So the computer shows you a world, and the computer shows you a formal sentence. Up the top there on the screen, there's a sentence in the appropriate formal language which happens to say, for all x, if x is a cube, then there is a dodecahedron to the right of x. In other words, for every cube there is a dodecahedron to the right of it. Oh, incidentally, the symbol for all x, you'll see, has this a upside down that I put at the beginning of Abelard. And the there is y has this e backwards that I put at the beginning of Eloise. And that's where I got the names from. The a upside down is simply for all, a as in all, and the e backwards is e as in there exists. So there on the screen you've got a sentence and a world, and you've got to play the game to decide whether the sentence is true in the world. You play the game by clicking on the screen where it says game, and the computer checks, is that really what you want to do? Do you really want to play that game? This computer's quite worldly wise. It puts the pressure on. You sure you want to play that game, it says. So you press OK, yes, you want to play that game. Now, the computer, remember, is playing Abelard, so its job is to choose a cube. And here what it's done, in fact, is to choose the cube C, and then it challenges you to make the next choice, and so on. And at the end of the game, either the computer will say, I've won, or it'll say, you've won. Do you want to play again? Well, that's what it's supposed to do, but I said it's worldly wise. It has all sorts of little tricks. One of the things it does sometimes is to tell you this. Evaluating this sentence may take as long as 303 seconds. I think that's my cue to finish. Thank you.